first, and then I'll do a brief introduction, and then Patrick will speak with a little time for questions. Now, today is the 29th of February, and it's a very rare occurrence, I understand. I'm reliably told that it is the only time in 1,000 years that it'll fall in the first year of the century, and we are very lucky because this is a very rare and special occasion that we have Max and Patrick here together. And they, I can say, are really two of the most important people in this country in environmental design and engineering. And their talks, in a sense, will complement each other, but they will give us a very rich sense of the possibilities and the history behind those possibilities in terms of the relationship of environmental design and architecture. And I say it like that because we should see that the two things complement each other as well. So Max is going to give you a wide range of all kinds of things. He's going to talk about the space for pipes, which is very, very important, and I'm afraid to say we often forget about. He's going to talk about a whole selection of things, some things to do with the evolution of ideas, these ideas from some historic precedents, and then he will continue to talk about certain examples from his practice as well. So thank you very much.
Well, thank you very much. Right. So then into that. Well, when I started becoming an engineer, I changed from being a physicist and thought that engineering was going to be quite difficult. And it's also different from science in that when you're a scientist and things seem difficult, what you do is you narrow the range of possibilities so that if you're doing an experiment and the temperature keeps varying in an awkward way, what you do is you make jolly certain that the temperature remains constant so that the other things can show up. But when you're an engineer, and indeed when you're an architect, you can't possibly do that because you have to take the environment as it comes. So, and then when you start off in your life, you take the environment as it comes. And I didn't know what to do, and somebody said, well, you could go and be a heating engineer. And somebody was called Leslie Martin, and he got me a job, and I didn't like that at all. And I then went to join Arup Associates and worked on a building called the Nuclear Physics Laboratory in Oxford, which is a very nice building, but there's nowhere in it for the pipes. And we had a horrible time trying to get the pipes into this building. And then Bob Hobbs and Philip Dowson, who were really the people who were running Arup Associates at the time, they got an idea about how to get the pipes into buildings. And they waited for a brief to turn up that would suit their idea. And the brief did turn up, and it was called the Mining and Metallurgy Building at Birmingham University. And this is a photograph of it. And the idea of it is that the building is constructed as a series of precast concrete tables. And you put all these tables down side by side, and then every now and again you get four legs together. And the space between the four legs makes a vertical duct. And then, of course, where the tables join together, there are some horizontal ducts. And if you want to put a couple of walls above the horizontal ducts, you can get a very big vertical duct. And when the brief turned up, we tried to analyze that idea to see if it would work. And one of the key issues was if you put a laboratory bench in the middle of a 20-foot square table, how can you get the drain out of the laboratory bench? All the other services are probably all right, but the drain's a bit tricky. So a little groove was made in the tabletop in order to accommodate possible drains. And the groove was about 50 millimeters deep and 100 millimeters wide, and that was done at feasibility stage. And then the building turned up with a whole lot of top knots on the roof into which you could put fans and things like that. There's another picture of it. Don't know whether that helps much. And the thing about this building then was that the ducts at 6 metre centres, I better get metric, hadn't I, looked as though they might occupy rather a lot of space, these groups of 4 columns. And anyway, the groups of 4 columns had to be fireproof, and they had little nicks in them to take a brick wall that were 2 1/4, 56 millimetres wide, so that was half a brick thickness, and you could just tuck the bricks into those nicks. And then the question was, how big did the ducts have to be? Well, we weren't going to analyse at feasibility stage the requirements for a laboratory for the services, but we thought it'd be quite good if a person could get their shoulders in and put the pipes there. So the dimension finished up about like that. And then we started building the building, and one of the problems about it was that you couldn't allocate space in every duct for all the services that a laboratory might have. And we thought, that's a pity, we better draw them all, coordinate the pipes in the ducts. And we did 1 duct, and it took 2 man weeks. And we thought, there are 80 ducts, so 160 man weeks is rather a tall order for a 6,000 square metre building. We'll let the contractors do it. And they did. Not very happily, but they did. And so the next building, which I haven't got any nice pictures of, was also by Arab Associates, was called the New Museums site in Cambridge. And I don't know if I can just point out slightly how it goes. It was on a grid that repeated like that. Arab Associates tended to build buildings on the grid. And so it's rather old, you see this. And so this and that is 2 grids. And then the slab spans this way about 8 or 9 metres and was made as a kind of series of T-shaped beams, so that you could get pipes across there. And this is where the laboratories were going to be. And then there was a zone here which could contain staircases, but more importantly, it contained a duct like that, which was about 5 metres by 1 metre. And that was big enough to say all possible services can go in that duct, so we can allocate spaces and draw them as though they were there, and then simply have a schedule to say whether that particular service is there or not. And the building is, I haven't got a picture of it, and it's pretty boring, but that kind of step forward in accommodating the services seemed to me quite important. And then there's a diagram here which shows that also in this zone you could get horizontal services running in this direction because it was a circulating space for people and they don't need much height. A couple of metres will do. And so that makes that provision. And that's a kind of history about how you get pipes into buildings. There was a lot of talk at the time about tartan grids, so that you have here a pair of grids, and then a big grid, and another pair, and a big grid, and so on. And in fact, Leslie Martin did the same thing for a building in Oxford, which was some biology laboratory, which also had a tartan grid. But his idea about the tartan grid was that not just that you got pipes in it, but you got lavatories and staircases and all sorts of rubbish of that kind. So that, I think, probably deals with pipes. Now, then I'm taking it for granted that I don't need to peddle the sustainability argument. Everybody here understands that if we go on burning all the carbon dioxide there is, the atmosphere will get poisonous. So we better not do it. And then we were all reminded of that in 1973-74, and I was asked to work on a university in Doha. Well, Doha is quite a hot place on the Arabian Gulf, like 46 centigrade is the sort of temperature you expect to get. And some people wanted to design this university so that it didn't need air conditioning. And that seemed like quite a tall order. But there was a precedent for it, which was buildings like this, which are called towers of winds buildings. So that this is a section through a part of the building, and it's got a tower here, and air can come in down here and ventilate this space and go up again. What you can't quite see in plan is that plan there. This is where the tower is built, and there's a crossed shape division, which is what these walls represent in the middle, to subdivide the airflow. This is definitely a valid precedent, and I believed so at the time. I went to Dubai last year and was told that the oldest tower of wind buildings in Dubai was built in 1923, when a whole lot of Persian merchants emigrated from Persia to Dubai and built these vernacular traditional buildings in Dubai. And that explains why they don't work very well, because they work much better in Iran, which is where the design originated. And it relies on having a pretty substantial temperature difference between night and day. Because the idea of these buildings is that during the day, cold air can sit in the bottom here and not be driven to ventilate out. At night, when the environment gets much colder, then the outside gets colder than the inside. You've then got a hot mass of air in the bottom here, which tends to go up by convection. And that's certainly the model for the university at Dubai. I mean Doha, right? They're all the same, these places. Better be careful, hadn't I? And so that's a drawing of the vernacular building. Now, this is a notional experiment to explain why the shaft needs to be subdivided. And it also, I think, makes it quite important to look at the precedents, because in a way, nobody would believe that you needed to subdivide that shaft. But I've never done this. Apparently, if you cut the bottom off a bottle and then put a candle in it in a pool of water so that air can't get in at the bottom, and you try and light it, it will go out. And the reason it goes out is because the air cannot move up the neck of the bottle and down and get any air in. If you subdivide it with a card or something down there, then the air will flow. And that explains why the Tower of Wind buildings need to have a vertical subdivision. And that is a piece of fluid mechanics which, it would be quite fun to set this experiment up on CFD and see what the CFD predicted, because the experimental results are quite clear and the CFD is another story. So there is a diagram which explains the idea about the ventilation of the Tower of Wind buildings. And then I started working on this building in Doha, and I thought, okay, well, we're going to cool the building down at night, and it mustn't get too hot during the day. So then it must have enough thermal capacity so that whatever heat gets into it during the day mustn't overheat it. And so you say, okay, well, what heat is coming into it during the day? Well, there are some people in there who are going to give off heat. It's a lecture theatre, so they're not going to have computers or anything like that. And the next thing is light. So the question is, how much light do they really need? Well, now, there was a traditional building in Doha which is constructed of mud and reeds. So you look at a building, here it is, it's a single-story building, and it's got a sort of spandrel here which is built up off the ground. It's then got these walls supported on these mud columns, and there is this sort of shape here which filters the light coming in. So light is reflected off the ground, comes up under this ledge, and is reflected several times and hits the floor. And that is a photograph inside it. I measured the light level in here, and it's 100 lux, when the bright sunlight is 100,000 lux outside. And you say, okay, well, maybe 100 lux will do. You see, these people, this building was built by people in the society using the materials they had available, and they produced that design. Now, if you go to Northern Europe, you find a design like that, which is also made of mud and reeds. And of course, the reeds are put up on end, leaned up against the roof to keep the rain off, and the mud's used in the walls. The walls there are pretty thick. If you go back a bit, the walls there are about 200 millimeters thick. And if the bright sun shines on the side of that wall, then you get a heat gain which passes through the wall as a wave. It's delayed by about 12 hours, so that it doesn't get through until the night time. And similarly, the wall is slightly cool 12 hours after midnight, so that during the day you get the minimum heat gain. I won't say you get any cooling, because that would be quite wrong. But then when you go to the Cob Cottage, you've got the walls about a metre thick. The windows, of course, are much bigger, because you don't have 100,000 lux bright sunlight very often in Northern Europe. It's usually about 5,000 lux for an overcast sky. And so the windows are bigger, and I guess the light level in there is not 100 lux, but nearer 50. But it's pretty amazing that these two sets of buildings, which have been, I don't know whether you can say designed quite, but they have evolved in step with a culture. And the people have made choices which go, if the windows are too big, then the temperature is too extreme. And if the windows are too small, you can't see. So we better find and optimize that a bit. And they optimize it and come across something which I think we have to say is about the same. And then you look at the code of practice for educational buildings in Britain in 1947, or 48 or thereabouts, which says all buildings have to have a 2% daylight factor. Well, 2% daylight factor on an overcast day is about 100 lux. It is 100 lux. So there's another pointer at the way in which society evolves solutions. And I think one can go on with this and look at 17th century buildings in Britain, or do I mean 18th century, my history is a bit poor, where the nouveau riche British traders, slave traders probably, got Italian craftsmen to come and build themselves some rather nice houses around the countryside in Britain. And they built quite tall rooms, rather like this one, with the windows going right up to the head of the window. Now, the explanation of that, I don't know what you think it is. There is an explanation which goes, oh, well, it's a cultural issue and we're just copying the Renaissance, and they were copying the Greeks, well, after a few steps in between, and that explains it. And Dionysus built tall buildings too. Or you can say, well, you've got a building of a certain depth, and oil lamps and candles are really quite tedious, so natural light's quite important. So let's have buildings with big windows and make the depth of the room comparable with the height. Now, you see, these are things going in where immediately, on environmental grounds, I'm beginning to say, why don't we do something about the architecture? I mean, I go further now and say, if you're building an office building and you want to have it properly lit, then what we know is that everybody has buildings that are called naturally lit. They're 6 meters deep. They have a meter or two height, horizontal, of windows down one wall, and the natural lighting is inadequate, so everyone turns on the electric lights. And we don't want that. So how do we stop having that? Well, there's a building in Mysore, which is an 8-meter double cube with a clear story all the way around it, with 4-meter square windows on all 4 faces. So it's 16 meters by 8 meters on plan, 8 meters high, and it's got windows with the head of the window 8 meters above the floor. the lighting inside that is absolutely wonderful, and you certainly don't need to turn any electric lights on. If you want to have low story height buildings, and you want them properly lit, then you better light them through the roofs. I've jumped ahead. Right. So now, having got to a Cob Cottage, we then go on through the history and come to a weaver's cottage, where people were forced by economic pressures to have looms at home. And if you're going to work on a loom, you'd better be a bit careful about, you need a lot of light on the loom, so that these buildings had very big windows on the first floor and are called weavers' cottages. And you can probably get 1,000 lux on an overcast day with a loom a metre away from the window. So that's a pointer towards getting high light levels for fine work. Slightly difficult, I think, because if you go back to the Arabian hut with perhaps 100 lux on the floor and say, I wonder whether people made Persian carpets in these huts, I think we'd better hope the answer is no, and they made them in tents where perhaps it was brighter. So that's all about lighting, and got me to the conclusion that for Doha we would design for 100 lux. And then you say, oh, well, if you're a lighting engineer and you put some lights up in a building, you say, how much light do these lights produce? Some number or other. Then you say, how much of that light gets onto the working plane and is useful? Well, the answer is something like a third or a half, which means if you want to light a space to 100 lux, you'd better provide 300 lumens per square metre by one way or another, and that's 3 watts per square metre of heat gain, because light is about 100 lumens per watt. And that's a figure which I think we should all know and remember. Just as 100,000 lux is bright sunlight and is 1,000 watts a square metre, a 5,000 lux sky is 50 watts a square metre, and the bright blue part of the sky is about 10,000 lux and is 100 watts per square metre. And those are quite useful numbers. So then here we are trying to design a university in Doha, and we're saying, let's have 100 lux inside. Then you go and you look a bit for some more precedents, and this is a photograph taken in Fez. Fez is a tropical climate, in a tropical climate, and the buildings are very densely layered over the desert, and then there are courtyards in them with cool coloured finishes, and the rooms behind the courtyard then look out into the courtyard and get less light. They're lit from the courtyard, and also because the building is a courtyard building, it's like a cup. At night, as a cup, it's full of hot air because the surroundings get cold, and then the ventilation, because the courtyard is big enough, you get air going out and coming in of the same hole, and then during the day the cold air sits in the courtyard and it keeps the building cool. And that, we're just keeping on going now, because this is a photograph in Shiraz where there is a pond, and there is a series of these. This is a courtyard alongside a market, and the courtyard is raised up so that you can sit comfortably on the side of this pool. The pool is raised up. In Iran, there's very little moisture in the air, so that the pool evaporates to the air and is comparatively cold, so that this thing is a cold radiator. You're in the shade, and it's quite a nice courtyard. The other thing is that as you go from a very bright environment to a dark environment, like going to the cinema here, for a while you can't see anything. If you're going to go from a university in Doha, from very bright light into a classroom which is to be 100 lux, you definitely want some time for your eyes to adapt. So you better go walking through a courtyard before you go into the dark room. You get a similar situation if you go into Mediterranean buildings where the shutters are closed during the day to keep the light out. And very often you go in and you go through a courtyard and then you go into the rooms behind and your eyes can adapt. You can halve the light level every 3 seconds. So I think if I've got this right, to go from 100,000 lux to 10 lux is 13 doublings, halvings of the light level. So it should take about 3 times 13, which is 40 seconds. So you better have a scale for the building which allows you to walk through it and take 40 seconds to go from the light place to the dark place. And so that was part of the Doha notion, that one would have courtyards and that one would walk through from light spaces to dark spaces. With all that, there was then a bit of a question as to what would be a comfortable temperature. And I found myself saying, well, I suppose 30 degrees centigrade might be tolerable. And I found there's a whole lot of comfort measurements, you see, which say actually 22, 23 centigrade is about the right temperature. But somebody went and took a special group of people near Delhi and discovered they thought 30 centigrade was all right. And you find yourself thinking, I found myself thinking, well, should I take that seriously? And then you try and turn the argument round and you say, well, if you're trying to design a building in Britain that doesn't need any heating, you might start asking yourself the question, well, how cool is tolerable? And maybe 16 centigrade would be all right. But actually, in neither case are the natives likely to like it much. And one of the problems about the sustainability argument is to whether just how hair-shirt we're going to be about it, and are we still aiming to make buildings comfortable or not? And I think we probably are. So that more or less finished Doha, and it looked like that, and it's the biggest air conditioning load in Arabia, despite all of this rather pretentious justification. So now let's get going, and because that introduced some of the ideas about light. Now, I then went and did a competition with David Morley for a cricket school in the MCC Cricket School in Lords, an indoor building. And it was to replace the indoor cricket school which is there, which is a portal frame, corrugated iron box with a whole lot of lights inside it. And the lights have to be on all the time because, after all, electric light's more reliable than natural light. And we thought, well, how are we going to get 1,000 lux on the floor in this building? And so one of the ideas was to have simply a black box. Well, that was definitely why we didn't want a black box. So the next one was, what about a translucent skin? And of course, we knew that the competitors were likely to be in the translucent skin business because we knew who some of them were. And we thought, well, the problem about that is that someone else is going to do it. That's the main problem. And the other, then, so what justifications have we got for discarding it? Well, the answer is that if you make this translucent skin able to give 1,000 lux inside on a 5,000 lux sky, it's got to have a 20% light transmission. That's perfectly straightforward and easy. But then when you've got 100,000 lux, you've got 20,000 lux inside. And that's definitely a bad thing, isn't it? And people certainly can't play cricket outside either. So that seemed like a problem, although more seriously, there's also a problem that if you allow the 20,000 lux in, then the building will get too hot. And it is one of the problems that we've tended to forget when thinking about natural lighting. And it's one of the problems that got forgotten when all the schools were being designed for a 2% daylight factor, and there was a tendency for them to get very hot. And in 1966, I think it was, the BRE invented a way of calculating how hot buildings would get. And it wasn't until then that it was possible to do that with any kind of, with anything that seemed sensible. In my first job, we used to do a lot of work with Richard Shepherd, and they used to say, how hot do you think this building would get? And I would work out a heat gain, and then I would say, well, if you have infinite ventilation, then the inside will be the same temperature as outside, and if you have a more realistic ventilation rate, it'll get up to 40 degrees centigrade inside, and there's something wrong with that, because buildings don't get that hot. And so in 1966, one began to be able to calculate how hot buildings get, and what I'm going to go on to talk about will show that those calculations work. So anyway, that's why we didn't want a translucent skin, and we finished up by saying, here is a north-lit roof light. Now, if you look at an overcast sky, then you've got 5,000 lux coming down on a horizontal surface, and about as much light coming from the north as the south, as the east or the west. It doesn't depend on the orientation, but most of it's overhead. If you then build a wall and you say, well, how much light is reaching this wall? Well, about half the light, because you can't see more than half the sky. And actually it isn't half the light, it's 1 over 2.5 if you do the mathematics properly. So what you can do is you say, if we've got this north light here, that is to say it's not seeing the sun, I don't know if you can see it there, then it's getting 2,000 lux on this surface on an overcast day. So if we want 1,000 lux on the floor, for every 1 square metre vertically there, we can light 2 meters this way. And so that indicates that if you want 1,000 lux, the ratio of the sawtooth has got to be 2 to 1, and we better ignore the fact that this is shading part of the light coming in. And of course, actually, there's also some reflection of the sun off that surface. So that produced a design, and it went through a series of transitions then, partly I think because David Morley liked curves, and so you've got these kinds of shapes building up. And anyway, it looks a bit like the Menil Gallery. And then we realized that we weren't going to get enough light in here, and the solution was to make, now let me get this right, that is opaque, so that if it were glass would be a north-facing roof light, but it isn't glass, that part is. And then we've got, right, and this part now is a whole lot of little north lights, so that the light which is coming in here partly is getting in from the sky, so that you get a good large amount of natural light. And this building doesn't need the lights on during the day. Oh, and there's a detail of this north light arrangement, so that light that comes in there from the north gets straight in, the sun is coming from here and is shaded. Then light which is coming from the north is also getting in here, and these are partly diffusing, and they allow a little bit of light as well to below. And that produces the light that's needed for playing cricket. Right, and you've seen a picture of the building at the beginning. So now there's some theory, because we've got, that's introduced the thing about how do you get enough light into a building. And of course 1,000 lux is quite bright. On the whole, nobody tries to design a naturally lit building to provide 1,000 lux. And the cricket school is not heated, so it doesn't matter that there's rather a lot of glass there, losing heat. And it has very big openings so that the heat gain from the light is dissipated during the summer. And anyway, the light only gets in from the sun late in the evening and early in the morning, because what you have to remember is at midsummer's day, the sun rises in the northeast and sets in the northwest, and you can get very badly unstuck, like the Tate Gallery at St Ives, if you forget that, which I did. So now, there's then some theory about buildings. This is an adaptation that I've made of a thing called the LT method for designing sustainable buildings. Now, the idea of the LT method is that passive buildings are daylit buildings. Now, if you read all the literature about the LT method, it doesn't really say that unless you read it quite carefully, but it means that. And the first thing you do to design a really good building, that is to say a building that doesn't use much energy, is to make sure that as much of it as possible is naturally lit. Then you consider what effect does that have on the energy consumption. Well, the way you do it is you draw this graph which says this is the proportion of the external wall which is going to have windows in it from 0 to 100%. And these are the energy use in kilowatt hours of primary fuel per square metre per year. And it doesn't matter a bit what the figures are. Of course, if there's no windows in the walls, then you need a certain amount of energy. These curves here are all the energy likely to be used. You need a certain amount of energy for lighting the building and for ventilating it, and a bit for heating it. But, I mean, actually, once you've insulated buildings to modern standards, you just forget it. As you put some natural lighting provision in, that is to say windows in the external wall, then naturally you need less electricity for lighting, and the energy used falls off fairly drastically. It depends, of course. If you've got a very brightly lit building, you get a curve like that, and if you've got a very dimly lit building, you get a curve like this. And then, as you increase the amount of glass in the external wall, you come to a time when basically you don't get enough extra light because it's after dark and you still need electricity for lighting. So you get a kind of a point of, you don't get any improvement as you improve the glass areas. But of course, as you increase the glass areas, you still keep needing some heat, and the heat load goes up. So the curves all tend to go on a slope like this, unless you've got double glazing, in which case maybe if it's very good double glazing and a warm environment, then the amount of heat required for the glass gets less and less. So that this is a thing called the LT method, and certainly when I first read it, it felt like a revelation. And I don't think many people have had that revelation, and so I put it to you that you should read it. Now, so that's enough about light now. This is a building which was designed by Brian Ford and Alan Short and Tony Peake, and it's a brewery in Malta. Now, Brian Ford, for some curious reason, came and worked in our office for quite a long time, and we made him detail pipes in a plastic moulding factory, which I think he hated. But on the other hand, there was a bit of talk, and he went away and designed this malt brewery, and this shows a section through it. You can see basically that there are some rooms. It's got double walls at the perimeter, various roof lights and ventilation openings. And the fact is that the inside temperature is about the mean of the outside temperature, which in Malta is quite comfortable. And it looks like that, which I think is a decent piece of modern architecture. So the next thing we worked on with Alan, oh dear, that's rather a pale. This is the Queen's Building at de Montfort, and we'll forget about that picture. That's a picture of it, and I don't know whether you can recognise it as a development from the Maltese Brewery, but it is. And the vertical shafts are ventilators, and there are also some rooms behind these funny things here, which have got very noisy machinery, which is supposed to be quiet and cool. But the main issue is that there are very tall shafts which drive the ventilation for an auditorium. Oh, I've forgotten which way to go. And that's a section through these auditoria. And the idea is that the shaft, oh look, this is rather a low shaft. I've got the wrong one. The shaft drives the ventilation because the air in here is warmer than the air outside. The air is then sucked in through a whole lot of louvers on the external wall, and in here, this space, there are heaters so that the air is heated as it comes in. Now, this is for a university where nobody talks about having air conditioning. In universities, you only have air conditioning if it's animals involved. So there's a picture of those shafts, and that's a picture of the air inlets. Working with Alan is pretty amazing because he draws very quickly and with fantastic facility. And maybe you think he sometimes draws a bit too easily. That is a picture looking up one of the shafts, which is lined with mineral wool so that noise from the outside doesn't get down to the lecture theatre. And yeah. And that is what happens when you test the temperatures in these halls. This is the outside temperature, and this is the inside temperature. This was done during a test when we decided to muck about with the controls. But basically, it does remain cooler inside than outside. And I think this peak is not the kind of thing which the design techniques predict very well. But on the whole, this sort of curve is perfectly in line with what the BRE discovered how to do in 1966. And it's in a digest which for some reason they've withdrawn from publication. So that is the Queen's Building. Now, we were talking to Alan Short about the vents at the Queen's Building, those things. And when we were working on that, we decided it was very difficult to be sure you could keep the rain out. And so we put all these louvers in and thought it seems to be that'll keep the rain out. And when you keep going, you look at it and you say, this is a diagram of what's going on. Air is coming up the shaft. In general, the wind blows, so the wind is blowing across here. The wind blowing over something reduces the pressure, so that you get a reduction of pressure because the wind's blowing over the top. But on the other hand, we put a lid on it here, and we're expecting the same airflow, the same velocity of airflow up here as we get coming horizontally in here, which means we're expecting more air to be going out through the leeward louver than we are expecting to come in here. And that means that the pressure inside this enclosure will tend to build up. And that's not what you want. You don't see chimneys like that very often. What you see is chimneys like this. Now this chimney you see, which is, if you imagine that as all circular, the wind is coming in this direction. When it hits that chimney, it's arrested, so the pressure rises. But when it blows across these open ends, the pressure drops. And as long as there's a bit of clearance between here and here, then you still get a low pressure over this outlet at the bottom. So these chimneys seem to be much better. And so we were explaining that to Alan Short, and I said, of course, the problem is that for the contact theatre, this scale of this dimension needs to be about 3 meters. And he said, great, and drew something. And in a way, that's, I mean, as far as I'm concerned, he's very nice to work with because of that kind of reaction. Now, there are other people who believe that technology is about performing miracles. Well, it isn't. And then if you start talking about the details about how it might do it, then you can see it's getting very boring. And Alan doesn't particularly want to know what the details are. He just takes what I've just said now as an opportunity. And not long after this, a drawing of this was published in BD, and it had a caption on it saying there's more to architecture than environmental engineering. And that's all it said. And Alan Short said, well, I'm absolutely delighted. To begin with, they don't need to say it's me because everybody knows it is. And secondly, they're wrong. So I hope you agree that they're wrong. And this is simply some studies we did inside the contact theatre. And I think they're very odd. They're said to be CFD, but here is a vertical shaft of uniform cross-section, and I don't really see what can be changing in it. And I do think one has to be very careful about computational techniques. You've jolly well got to understand what's going on. We did another CFD analysis on a building where we were predicting how the energy came in through a roof light and hit a floor, and then how the building was ventilated to take the heat away. Now, we ran the CFD, and the floor temperature got up to 400 degrees centigrade. And we thought, oh, there's something funny about this. And then I remembered a lecture I'd had when I was doing physics, where somebody had described how you get a mirage in the Sahara. In the early morning, the sun gets up and the desert heats up. And you get a hot layer of air sitting on top of the desert. Oh, well, that shouldn't happen because there's convection currents which immediately should take place, and cold air should replace the hot air. Well, it doesn't, because it doesn't know where to start. And for a while you get an unstable situation, but the instability doesn't develop. Now, when you're doing CFD, what happens is that the calculation technique takes groups of points, and it takes, let's say for the sake of argument, 3 points, and it says the middle point should be somewhere in between the 2 outside points, and like it should be halfway between them. So it goes round and calculates what the middle point should be at, and then corrects it and puts a new answer in for the middle point. It goes on doing that across the whole field, and it goes on doing it on and on and on, and every time it makes sure that a whole lot of other pieces of physics are still holding, so that when it relaxes the points, it's called relaxation, eventually you get a solution which looks good. And you can do a whole lot of mathematics to show that it ought to be good. But actually, you see, if you start off with all the points the same, it might take a very long time before it notices that some of them need to be different. And usually that starts at one edge, and the relaxation works then across the calculation field. But actually, it takes a very long time, and there's a great many calculations to do, and mostly people get fed up before it's got to the end. And in fact, you program the computer to tell it to stop before it's got to the end. So that what was happening with this thing was that the heat was hitting the floor, there was no way of it getting out, and so it got very hot. And we then reran it by putting double the heat gain in to half the nodes, so that adjacent nodes were then definitely having different conditions. And very quickly it got an answer that we could believe. So as we could believe it, it must be correct. And that's another problem with CFD, which is that you go on mucking about with it until you can believe the answers. And that's not, it's not that's definitely not a scientific technique.
Waste of money. Waste of money.
No, it's not a waste of money. It's because at the same time as these, you've got to believe in the answers, right? And you better believe that the calculations that are being done are sensible, and they'd better make a whole lot of other things, conditions, work. So it also, you can get pictures like this and it can produce ideas. You can look at it and say, oh, I don't want the air to do that. Why doesn't it do this? And then that's an idea which affects the design. And that's so, it's like painting pictures, which is what architecture's about. And I think that's probably my cue to stop. Oh, look at that. Right. So now, let me just close this down. Not supposed to have done that. No. It's like that.
Technology transfer.
There you are. Right. Look, there's your wonderful little thing. Great.
Thanks, Max.
Yeah.
While Patrick's setting up, thank you very much indeed, Max. At the end we'll have an opportunity to ask some questions and raise some points. I'm very pleased to introduce Patrick Bellew as well, founding partner of Atelier Ten, and he is going to talk about influences on an approach to environmental design, perfectly on cue. Mainly historical and animal influences, maybe some vegetable and mineral. And then he's going to talk about thermal storage techniques, talking a bit about the Earth Centre and also about the Federation Square project in Melbourne. So projects in the UK, Germany and Australia. You ready to go?
I'm ready to go, miraculously.
Thank you.
Thank you. It's very tough act to follow Max. I'm just going to try the... I wish I hadn't touched that now. Try and get both of them on at once. Just hang on a second. There we go. I've actually applied for a job at Max's practice once, and nearly went to work there. Just geographically didn't suit me at the time, and I've been a huge admirer of his work for many years. Our work has kind of veered away in slightly different directions in some ways, which I think I'm going to take you through this evening. I came into environmental engineering quite by accident and entirely through the influence of a single individual who was Ted Happold. I put environmental engineering down as a kind of afterthought on my UCA form in 5th place, beyond the various other courses around the country, very much not to do with engineering. And I went down to Bath just thought it was a nice day out to go down, get away from school and go down to Bath for the day to be told about environmental engineering. And Ted produced a 2-hour lecture. He'd just finished doing the Beaubourg Centre in Paris, and he'd worked on the Sydney Opera House. And he produced a lecture that just stirred the soul to such a point that I came out of his lecture saying, that's what I want to do. And Max and I were talking before we came in tonight about what it is that makes people environmental engineers. And the answer is we don't really know. It seems to be people get into it more or less by accident, or frequently family or other connections. It's not the kind of career you get into by accident when you're filling in your UCA form, that's for certain. And that's witnessed by the fact that many of the engineering schools around the country are closing down due to lack of interest. Single figure entry. One person joined the course at Reading this year, so they shut the course down. It's a very difficult area to get to recruit into. And so there are many architecture graduates coming out of university, all of whom want the support of environmental engineers, of good environmental engineers, but actually our system is not supplying environmental engineers anything like the numbers that we need to answer all of your needs in the future. And so it makes it doubly important that architects understand what Max has been talking about building physics, because generally a lot of what's good in environmental engineering is intuitive, and it's about the architecture. If you go right back to Victorian times, and that's studied by people like Rayner Banham in his work, architects used to be responsible for environmental engineering up until probably the 1920s, when Willis Carrier discovered air conditioning, or perhaps a bit before that when there were a few ventilation engineers around. You were responsible for creating the built environment, and it was only when we came along and said, hey, it doesn't matter, we can cool it. It doesn't matter how big you make it, how much glass you put on it, we can cool it. And so we spent the next many years, the engineering was a muscle-bound profession where we're looking at how big a load per square metre can we actually deal with. Now clearly, Max has said that we can take this for granted, and I think that you understand this, but I think that these are recent photographs of the hole in the ozone layer. It is a huge issue. Buildings consume 50% of the energy used on the planet, and you're responsible for designing those buildings. How are we going to achieve a 10% reduction in CO2 over the next few years unless our buildings make a huge inroads into that? And it's not factor 2 or factor 3. It really is this thing about factor 4. You've got to be doing things a multiplier of times better to make your buildings have any impact on this kind of problem. You often feel in doing what we do, and I'm sure Max feels the same, you feel like you're tilting at windmills. Everything that we do is a tiny part of this huge problem, but it is nonetheless a vital part of it, and it's a part that architects have an enormous role to play. And I don't see myself as a kind of tree-hugging environmentalist in any way at all. I've never really been into that sort of movement, but what one is starting to realise is that there's an acceleration of change that is witnessed. This is off CNN yesterday, the floods in Mozambique. Now that's not just happening by accident. This is global warming, and this is climate change that's happening. And it's changing in Mozambique, it's changing in the USA, where you've got very big, very mature trees that have never seen a tornado that big before come through and hit them. And those are signs of global change. Also, another change, which I think is equally important, is biochange. Things that we are doing to the planet at the moment are causing fundamental breakdowns in biosystems, and it's particularly acute at the North and South Pole. The polar bear cub population is dying, is reducing in numbers simply because the pack ice isn't around for long enough anymore for the adult bears to kill enough baby seals to feed their young on, so the young aren't surviving in such great numbers, so the population is dwindling. And the penguin on the left is also suffering now because the ice shelf is receding in the southern Antarctic. So although you don't have to be an environmentalist to be interested in these issues. These are issues that are going to affect us all, and in a really big way. And I think Buckminster Fuller had it just about right when he penned this phrase about Spaceship Earth. And we don't really know, we don't really have the answers, but all we can do as practitioners is to try and develop our methodologies so that we improve the way that we approach the problems. I'm going to talk a lot about thermal storage, maybe not too much, but quite a lot about thermal storage. And Max has already touched upon a lot of the issues. I mean, thermal storage is an intuitive thing, is as old as architecture. On the right, troglodyte caves, people taking shelter, looking for this attenuation of the daily swings from day to night in temperature. And on the left, remains of a Roman hypercourse, which was used as part of an underfloor heating system. Diagram from the Villa Costozza in Italy, where a cave system is used as part of an underfloor ventilation system in houses, so a prevailing wind pushes down through the caves and provides passive cooling. And the indigenous architecture of the Arabic world, which is very much where one gains inspiration from, perhaps particularly looking at thermal storage, where the main idea is to attenuate and store heat gains from day to night to try and make the days less hot and the nights less cold. And that's a key part of the kind of environmental models that I'm going to show you a bit later on. So the importance there of night cooling is a big issue, but there is an issue about, in our climate, how you have to limit how much you do night cool, because you get a problem. You cannot overcool buildings. What you don't want to have to do is put the heating on a summer morning, having had a very cold night, because everyone comes into the office and it's 15 degrees and it's freezing, so you've got to switch the heating on. Clearly, one has to find a way of dealing with those sorts of things. And a particular area that I've been working on in the last couple of years is what we call decoupled storage. Sounds terribly dull, but it's basically taking the storage out of the room and putting it somewhere else. And I'll show you what we've been doing at the Earth Centre and Federation Square on those subjects. And thermal storage can also be part of great architecture. I mean, Corbusier was a great exponent of environmental design in many of his projects. And this is a project, my first project with Ted Happold and Fry Otto when I left university, which is a diplomatic club in Riyadh, which kind of was very much a redefining building in Riyadh. It was a very mechanical building. It didn't have Max's passive wind stack ventilation systems, but it had big thermal mass, small windows, lots of kind of solidity to it that made it a very successful and low energy building. I always sort of kid a bit about where environmental engineers find their inspiration. There's a few from indigenous architecture. As architects, you perhaps can look to your peers and to history for your architectural influences, whether it's Corbusier or Louis Kahn for his excellent hiding of ducts and pipes, and those sorts of people. But there's a massive body of work in architecture that can give you many clues. In environmental engineering, it's not quite so easy. But the termites are my favourite example of animals that produce environmental systems for their buildings. This is the nest of the compass or magnetic termite in Western Australia. They're called the compass termite because they orientate their nests exactly north-south. So they present this very thin edge of nest to the midday sun, so that they minimise the heat gain. They have the height of the tower is just like Max's wind towers, really, is to catch the breeze that's moving above the tundra, and the Bernoulli effect across the top of the stack pulls air out to ventilate and pulls air in through a diaphanous. This microphone stand always catches the light. Pulls air in through an edge here and down into an undercroft where the ants live. Now, termites are white ants. They're this big, and they're completely blind. And they build by intuition and some sort of biochemical reflex that we don't really understand. But what they understand is they understand physics. And there's a lesson there for us all, that you've got to make your arrows do the right thing on diagrams, or they just, if they defy the laws of physics, they probably won't work. This is the nest of the Barossa termite in Africa, which, if you watch Life on Earth, was the nest that David Attenborough and his film crew were climbing around inside when he was presenting a program about environmental control. And the Barossa termite the nest is structured entirely around one motivation, which is to keep the queen, who lives in the middle, at 30 to 31 degrees C all the year round, because that's the temperature she likes to be at, and she's the boss. And you have certain of the animals have a job in their life, which is to be like a volume control damper. They block and unblock these large holes inside the nest in response to temperature stimuli from the centre. So we're not quite sure how that works. It's biochemical in some way, but the signal goes out and says we're too hot or too cold. So if it's too hot, they unblock the holes. The stack effect increases. The wind going across the top might help to drag some more air out of the nest, and air is brought down into a cool cellar that's down underground. And in that cool cellar is a big spiral. There's a close-up look. In the cellar is a sort of spiral fin, which there was a film. David Attenborough and his film crew were down in here, so that's how big it is. And again, these are the same size as the ants in Australia. The moisture from the nest runs down in these spirals, and you can see the deposited salts there from the excretions of the nest, and that provides an evaporative cooling effect. It provides the moisture for a cooling effect. Now, if in periods of severe drought, the animals have been observed, they all come back, they stop going out searching for food, and they come back to the nest, and they go up and down to the water table, carrying little leaves or bits of leaf with water on, to act as to increase the evaporative cooling effect inside the nest to maintain the temperature. As the temperature drops, they block the holes up, and at night the holes are almost completely blocked, so that the heat from the day is retained inside the nest. They also have a central heating system, which is incredibly complex and relates to the growth of mushrooms on beds of chewed wood. Certain of the ants have a job which is to secrete an enzyme which stops the mushrooms from germinating during the daytime. So at night, when it starts to get cold, they stop secreting the enzymes, the mushrooms germinate, and as mushrooms germinate, they release heat, and therefore provide the central heating for the boilers for the system inside the nest. Now there's lots of ideas in there about thermal storage, about evaporative cooling, about passive stack ventilation. That's the queen there, and these are the workers helping her, and she produces many thousands of young per day, I gather, to sustain the large population inside the nest. But there are so many influences there for the environmental engineer that it's kind of irresistible. But what's most important about it, I think, is that it's intuitive. And good environmental design is almost always starts with intuition. Something that looks like it works, I say it again, will often work. There are lots of things that you have to test, but you have to look at it and see if it looks right. And so Max's diagrams of buildings that are made entirely out of glass, you've got the graphs that show that buildings that are made entirely out of glass probably aren't energy efficient. You look at them and you think, well, can it really be that a 4-metre high north-facing glass wall, no matter how many layers of glass and how many clever blinds it's got in it, can it really be energy efficient? Is that actually a sensible way of doing things? And besides which, in a modern office, how are you going to see your computer, say in the new Lord Mayor's office? How is anybody actually going to see a computer with glass on all 4 sides in this new sustainable building? I just posed that as a question that I wasn't going to answer. Max talked a little bit about schools, and this is a school that we finished last year at Great Notley. It's the so-called Sustainable Primary School, where we were aiming for a daylight factor of about 4%. And actually the facade is pretty much geared around daylight. What we have is a clear-story window up here, a lower window down here, and then these folds in the roof are designed so that the classrooms each have a high-level light, a low-level light, and a top light here. It's a bit, the picture for me here, it looks a bit compressed, but I think you can probably get the idea. This is quite a relatively deep classroom. But what you get in the classroom as a result of that combination of north light and south light is a daylight factor that's around 4%. That solid panel, if we'd made that glass, would have been too much light, too much sun, too much heat gain. And so what we provided was a system that's very much about daylighting. It's also about ventilation. There's a high-level vent that opens here and a high-level vent that opens here. So you can purge the heat away from the high level of the space to reduce heat gain, or to get rid of the heat gain and stop the build-up without it causing drafts down at low level. And then there's also a second layer of windows down here where the teachers can actually open the glazing on very hot days to get air through. So a very simple classroom diagram that grew very much out of the work in the 60s and 70s on classrooms and produced a building that actually has no thermal storage in it. It's a very, very lightweight building. And the other point I wanted to make with this is that it's not always appropriate with buildings to make them very heavyweight. A school building is actually only in use for 9% of the working life of the building. That's the number of hours of the year that most classrooms are in use. And so it doesn't make a lot of sense to have very massive storage systems. It actually makes sense to make things fairly light, fairly responsive, but the things that deal with the daylighting and the heat gain and the ventilation issues in just a very simple way. And the results, in some ways, might be perceived as slightly odd. This roof here, it looks kind of quirky, but it's actually all about the daylight diagram, and it's been very interesting developing up that model with the architects and watching how the input of the environmental engineer has fundamentally altered the way that the building is perceived. I don't think AHMM, who were the architects, really felt it was going to turn out this way when they started designing it. The grass roof is intended as part of the sort of the CO2 balance for the school. The walls are 300 mil thick of recycled insulation, breathing wall construction. There were going to be photovoltaics and wind towers and all sorts of wind generators and things on this school as part of the kind of sustainability argument for renewables. But actually what it was felt to be was it's an on-cost, on a DFE cost target model for building buildings of this type, and we could actually replicate this around the country as a very low energy building without having to put all those things on it, and so it's kind of affordable as a transfer around the country. To get moving a little bit onto the thermal storage and perhaps what are good examples of low energy buildings that are currently around in the UK. I knew that Max would have shown some of his, so I haven't put his in. I've put one of yours in actually. But this one is a very interesting building by Rab Bennett's, which does all this thing about balancing daylight, the way the facade works. It's quite pragmatic. It says, I want the light in here, I don't need the light in here, therefore I'll make that a solid insulated panel. I want to be able to bounce the light into the space. I want to avoid direct solar gain because my thermal storage slab, which they've got in here, can't cope with that sort of heat gain. So there's lots of kind of things about the scheme that are entirely environmentally driven. This high-level window here, which comes in across here, is all about night cooling. It's about letting air run across the slab at night to get this daily temperature, this daily cooling, nighttime cooling, for the following day. I'm going to zip through these, but they show you some of the principles. And the BRE building, with its stack effect chimneys, which is interesting in a different sort of thermal storage technique, where it's combining a fairly complex natural ventilation model with the ability to produce a deeper plan building. One of the limitations on office buildings is that once you get beyond the first 4.5 metres, what happens to the poor legal secretary or paralegal who's stuck in the middle of the floor with the partners by each window, and you've got these poor people sitting in the middle. So this is a very interesting model because it looks at how you can deliver naturally ventilated air into the centre of the building. And I mean that's the reason for putting the slide in, because it's a combination of quite complex thermal storage techniques with natural ventilation and with integrated lighting. And I think it's a very successful model in doing that. Just off this slide here is the Queen's Building, which Max did, and we followed on after the Queen's Building with Eva Jurichner, architects, looking at their new library, the Kimberlin Library, an extension to a rather ugly 60s block that was stuck here. And the university's brief to us initially was, as I said, that as a university we're very into natural ventilation. We believe very strongly in natural ventilation. And we took the brief and we looked at it and we talked with them about the usage of the building. And what they said they were going to do was to put 1 student per 4 square metres with a computer. And they said they were going to put them there from potentially 6 in the morning or 7 in the morning until 10 o'clock at night, all through the year. So we looked at the natural ventilation model, particularly the winter model, because actually when they say all through the year, they don't really mean the summer holidays, because mostly they're not going to be there for sort of July and August. So the big issue is about the winter heating when the library is busiest. And we said, well, actually what you've got here is a good source of heat. You've got students, free heat, so we'd like to get something back. We've got computers, which are, you're going to have them on, so they're free heat, and you've got the lights to some extent, although we have tried to work on natural lighting on the building. But when lighting is available outside all those hours of daylight, all those hours that are outside the hours of daylight, we're going to have lighting loads as well. And it seemed a shame to throw it all out the window. The building was narrow enough just about to do a naturally cross-ventilated scheme, perhaps with some central chimneys. And so, but they didn't want air conditioning, and we were concerned about how we'd avoid overheating. So after lots of looking around at different sorts of systems, we came up with a solution which is called Thermodeck, which is an building-integrated thermal storage system, which essentially uses the ceiling, or is a series of precast concrete planks. Here they've been rendered, and the ceiling, the precast concrete planks have holes in them, and we join the holes together and push the air backwards and forwards through the planks. So there's a manufacturer's diagram of what actually happens. You've got an air duct which sits in the bulkhead in the middle. You connect it to the slab and the air goes backwards and forwards inside the slab, and that acts as a big heat source or heat sink. Now, the difference between that and a flat slab or even a slightly profiled slab is that when you look at cooling a flat surface, you're only in an average day going to impact on maybe the outside 25, 30, 35 mil is your heat sink as the heat moves in and out of the concrete. What the Thermodeck does is it actually opens up that 25 or 35 mil all around all those holes in the cores as a potential storage point for heat or cooling. So in the wintertime, you can use it as a stabiliser, as a capacitor to store the heat gain from when the students and the computers are there to when they're not, or when they're there less, so you avoid this daily swing in temperature. And in the summertime, you can cool that slab down at night to maybe 19 degrees, so that it acts as a cool surface over your head, but then acts as a cool conduit for air to come through the following day. And the storage capacity of that is somewhere around 60 watts a square metre of cooling load. Now, if you add people and computers and all those sorts of things together, people, it was very exact, people, computers and light together, we get to around 60 watts a square metre. If you let too much sunlight in, you can't deal with the perimeter loadings, so you have to keep the sunlight out, or certainly the summertime sunlight out, although you can let daylight in. And you also have to try and deal with the fresh air load in some other way, and we do that with an evaporative cooling system on the air plant, which I'll come on to in a minute. So what that does is to, and Max showed us a graph of the other thing. I'll show you that in a second. This is the same, pretty much the same warm day in Leicester. We must have gone similarly, about 31 degrees, and that's the outside temperature going up and down. The blue line is the air going into the hollow core on the Thermodeck. The green line is the air coming out of the hollow core on the Thermodeck, and the red line is the space temperature inside, even with all those people and the computers inside. And that building's been monitored now for some time. And the temperature in the summer stays at around 23. And in fact, you can drop it more if you can take a cooler air supply temperature in the summer. So in terms of the summer cooling capacity, we're able to actually achieve virtually air-conditioned conditions without any mechanical refrigeration, even with that density of students, which was actually much better than our calculations suggested it would be. Our calculations suggested we would get up to 26 or more, but we never have done. The other thing about this is that because of the heat recovery on the plant, they switched the heating off from the building last year completely, and it didn't actually affect the temperature inside at all. The computers and the students, it's so densely used that the recycled energy from the computers and the students mean that they don't actually have any heating on. But what you are paying for is the energy for the fans, because you're having to drive the air through the system and drive the air through the planks. So you have an energy cost in running the fans, but you're left with virtually no heating energy cost at all. And we're just finishing a building in Winchester which uses the same system. It's with Field and Clegg. It's a little college building for King Alfred's College, about 1,100 square metres, the diagram here, it's slightly different to the De Montfort in that it's got a single loaded duct. It's got duct down one side, and then the thermodeck planks go across this way. But I put it in because it is actually fully, quite heavily glazed on the south side. You can see here there's a lot of glass, but we've worked pretty hard with them on the shading so that we keep the peak solar gains out. There's also an internal blind to deal with the glare because it's a very highly computerized environment, so that on certain conditions they need to deal with the glare. But we've kept the solar gain pretty much out, and the thermal system works as the Leicester scheme. Now I'm going to do something very brave here and show a piece of plant at the AA, which is not something that happens very often. This is the diagram of how it works. There's a blower unit here with a cooling system. I talked earlier about the evaporative cooling. This is the sort of high technology, high efficiency plant units that we're using, which, although it's not natural ventilation, it's a mechanical system, but it's a high efficiency mechanical system. It uses very little energy. So we have very high efficiency fans sitting here and here, which is extracting the air here, supplying here. And what happens is, to get the extra cooling effect in the summertime, we pull the air out of the building, and it passes this way and passes twice through a heat recovery plate, a box of plates, effectively. So the air goes round that way. The fresh air, meanwhile, comes in this way and goes through the other side of the plate. So the air doesn't actually touch. They're on counter two sides of a plate. And we spray cold mains water over the air that's going out of the building. And that cools the air. So the air's coming out of here at about 22, 23 degrees. And we push it through here, and we spray water at 10 degrees over it, cool it down to about 16 or 15 degrees as it goes through that first set of plates. So then the air that's coming in, even if it's 28 outside, is being pre-cooled as it passes through here and comes off at a temperature of around 21 degrees, which then means it doesn't impose any additional cooling load on the thermodeck planks. So we've dealt with the solar load, we've dealt with the air load, and the thermodeck planks are dealing with the load from the people and the lights and the equipment. And so we've therefore got a system that's pretty much in equilibrium in the summer, although we are paying to run the fans, we've sized. What we do then is we apply what we call this factor 4 thinking to the way the ducts are designed and the way the pipes are designed, which is to say that if you increase the size of a duct by something like 10%, you reduce the energy that's required to drive the air through it by perhaps 30%. And so if you actually slightly oversize all the ductwork, you can then reduce your energy consumption by 30, 40, 50%. So these fans are sized on about half of the kilowatts per meter cube that a normal fan system is. What's amazing about this is that is the boiler for the whole building. And that boiler comes on for about 3 hours a day in very cold weather and not at all the rest of the time. So, I mean, they've been watching it. We ran the system up first in December, and they've been observing it every day through on the BMS through, and it literally is running 3 hours a day, and it's about a 40 kilowatt boiler doing a 1,000 square meter building. So it's a fairly significantly low energy building. But what you are paying for is blowing the air through that unit. So it's not zero energy; it's just very low energy. Before I leave entirely off the thermal storage, I wanted to talk about a project we've just finished also in Germany. This is some low energy, very very low energy housing in Hanover. This is the first design studies that were done for it. One of the reasons that people don't build very low energy buildings over here is because there's a difference. The people who procure buildings, if you look aside from universities and places like that, people who procure buildings mainly don't pay the bills to run them. Whether you're Berkeley Homes or Stanhope Properties, you don't normally pay the bills. The guy who moves into the building pays the bills. And so that means that there's no real inspiration for anybody who's building buildings to do anything other than comply with the regulations unless they have some unique marketing proposition. So that's why most of the buildings that Max and I and people have done that are low energy buildings tend to be either university buildings or buildings where the owners are going to run them. And you don't find a lot of movement in the speculative market towards this sort of thing. What they've done in Hanover, this is a site on the edge of the Expo, which is the Environmental Expo in Kreuzberg, just outside Hanover, is they have regulated the hell out of the schemes. We have to achieve, the normal house in Germany will consume about 120 kilowatt hours a square metre a year. We've had to demonstrate that our housing scheme will not use more than 50. And when I say demonstrate, we've had guys, I don't know if Jochen's here, the guy's been doing all the analysis work, but they've come back with questions over 1 centimetre difference in disparity in the sizes of windows that we put in our models and this sort of thing. I mean, they really have checked it to death. So we've had to prove we've achieved only 50 kilowatt hours a square metre a year. We took the conventional model for a low energy housing would be, this is south down here, would be a north-south facing array of buildings, because generally it's felt that south-facing flats produce the most energy efficient solutions. We actually turned that around a little bit, and we've said that if a block of flats is on the east or the west, it still gets sunlight for part of a day. And if it then shares a common space between the next block of flats with some kind of what's become known as the microclimate zone in between, then maybe we can find a more energy efficient model. So the heat loss is only through these outer faces, not through the inner faces, because the microclimate zone is more self-regulating. So our early diagrams, I don't know if you can read much of this. This is a winter diagram. Basically, it says that's the microclimate zone here. We have on the roof a triple skin hostaflon roof, which has a moving panel in the middle. And so this panel is fritted with it's got a patterning on it, and the panel on the top has got a patterning on it. In the winter time, we leave the central panel pointing downwards, and so we let the sunlight come through into the space where it hits massive concrete walls on the inside of these flats, which are insulated on the inside. So you've got concrete here, insulation, then the finish. In the summertime, that skin moves up to the top surface, and it's designed so that the fritting matches up when the skin's in the upward position, and so it becomes a complete reflector. So it reflects all the solar gain, or most of the solar gain, away from that top surface, giving a much reduced solar gain factor, so that we don't then overheat the atrium and result in overheating in the apartments. Each of the apartments has then got I've just hit a button. It's mechanically ventilated, because in terms of the regulations, we couldn't have living spaces opening out into the microclimate zone without having some other source of fresh air. So they're all mechanically ventilated, with a high efficiency heat recovery, which runs in the winter, and again low specific air volumes. And what's the result of it? It's now nearing completion. There's the hostaflon roof flying over the top, 300 millimetre thick insulation on the outside of the walls. But we've managed to achieve quite a high level of glazing on both the east and west sides to get good daylight into the apartments. It can be filtered in the summer. The blades on these haven't yet been set up, but it'll be filtered in the summer, so you can push a shutter across in front of the windows in the summer to keep the direct gain out, but you can push it across an opaque area in the winter so that you allow solar gain into the apartment in the winter. And what's amazing when you go inside the microclimate zone, which I love that word, it's great, is how translucent that roof is. That's 3 skins of test-cell foil, which is giving around about 80% translucency. So inside it really does feel pretty much as though it's brightly daylit, but with obviously a much calmer environment without the wind, the snow and the hail. Now, just as a quick comparison, in the UK, I guess housing might be around 120 kilowatt hours a square metre a year as well. A typical house would consume something like that for heating and what have you. These are 50, but it gets down to minus 15 in Hanover for about 2 to 3 months of the year. So it's a hell of a lot colder out there than it is here. It's been monitored and tested, and so far it's performing very well. Now I don't know how much I'm doing for time. I'm just going to take you through now this idea of labyrinths, of decoupled thermal stores. And the first project I'm going to talk you through is the Earth Centre in Doncaster, which is a Millennium project designed by Field and Clegg architects. And the gallery, the building I'm going to talk about mainly is the Arrivals Building Gallery, the Planet Earth Gallery. This thing over the top here is a photovoltaic array of 500 square metres of PV, which is currently being built. It wasn't built in time for the first summer of trading. And here is also a little cafe building, which I'm not going to talk about. There are lots of other interesting buildings on the site. There's a building by Will Alsop, which houses a living machine, which is a sort of sewage treatment, a biological sewage treatment plant. But I'm going to specifically talk about the Earth Centre. The building was intended, its brief was to become a national centre for education and enlightenment in the field of sustainable development. So it was entirely appropriate that we should come up with a low energy solution. So here again, we're not talking about clients who are looking for building regs type solutions. We're looking for benchmark buildings and very, very low energy targets. Now, this graph shows typical buildings. A poor gallery building in the UK might use that much energy for heating, that much for cooling, and lighting and other. What our target was to get down to something like that for heating and something like that for cooling, which would just be the fan energy, to try and eliminate air conditioning altogether. There are still criteria that you have to meet. As Max said, you've still got to produce comfortable environments. We can't be responsible for producing environments that are fundamentally uncomfortable to be in. So criteria number 1 is that the comfort and air quality has to be maintained. But the first designs that came up, that the site is an old colliery spoil heap on the edge of Doncaster, and it straddles a fault. And so the structural engineers who were Atelier 1 had something like a 1.2 metre thick raft that was going right across the site. And in our first discussions, we thought, well, what we really want to do is to get the air in at floor level, because displacement ventilation seems like the right way to get the air in. And so we sort of started to talk to them about, can we hollow out this floor and make it a composite slab? So we've got two, top slab, bottom slab, and linked together by concrete walls. So this was the first sort of doodle that I sent to Peter Clegg. And we sort of started to think, well, how can we maximise the surface area under this floor? Should we start putting in walls? Should we start putting in this was an idea we might use traffic cones, because they were looking to use a lot of local labour. Could we take traffic cones, fill them with rammed earth, and then spread them out across the floor to increase the surface area so that we maximise the sort of thermal capacitance of the structures? But the honeycomb composite slab suited the structural engineers, and so we started to develop this idea of a labyrinth. And an important intrinsic part of that is the idea of displacement ventilation. And I'll just bore you with this just for a minute, because it is quite important when you're looking at low energy solutions, because when you bring air in conventional cooling systems at ceiling level, a conventional air conditioning system blows the air in from the ceiling. Witness one ceiling diffuser. What that does is it takes all of our contaminants and our wasted air and our heat, and it mixes it back up in the room. And so that air has to come in very cold in order for you to feel comfortable at the level you're sitting at. It has to come in maybe at 12 degrees to achieve you comfort at something like 21. The idea with displacement ventilation is you put the air in at the floor level at maybe just a couple of degrees less than the environment that you're serving. So it's at 18 or 20 degrees if you want to try and achieve 20 degrees. And so then a temperature gradient works with the heat of the room, and so at the top of the room, the highest point of the room, it's very warm. And you can extract it away, but you can get a comfort quite easily at this level. Now why that's important is because with the English climate, the outside air temperature is warmer than 12 quite a lot, but warmer than 19 for many hundreds of hours less per year than that it is warmer than 12. So what you get is free cooling for up to an extra 700 or 800 hours a year when you can push outside air straight into the space without having to pre-cool it. So displacement ventilation in many applications provides you, as long as the ceiling heights are high, and I should say these galleries were 6 metres high, provides you a very good way of getting low energy air supply. So as the design developed into these labyrinths, these underground labyrinths, this shows what happens at night. We've got a high efficiency plant, very similar to the one at the diagram I showed, the machine I showed you earlier, sitting up here, and it pushes air into this undercroft, and it runs along this long duct that runs right the way along here, but it runs at about half a metre a second, so it's really slow, very, very low energy consumption fans. It goes backwards and forwards through these cells, and it cools them down. And we don't put it into the room at night, where we cool the room down at first. First off, we cool it down to the temperature it wants to be at, and then we stop. We shut the room supply off by just shutting some dampers, and the air is then taken away and thrown out, back out to outside. So we can actually keep the labyrinth cooler than we can keep the room. So by decoupling the thermal storage from the space, we can keep it cooler. It's also true to say that in a very large volume space, doesn't matter how massive you make the walls, because an individual standing here, this is 20 metres front to back, an individual standing here is such a long way from the surface, it doesn't really matter how massive the surface is, it's not going to feel like a massive space, it feels like a lightweight space. And so that's the idea of the labyrinth, is that we cool at night, and then the following day, we can then push warmer outside air through the brick walls. It cools down as it comes through, and then it gets run back up this duct and is delivered through diffusers in the floor and spreads out across the floor where it absorbs the heat gain from the occupants. When the load is satisfied, or at the winter time, we can then open a little damper and a door here, which that damper shuts, that one opens, and the air runs straight down to the spaces. And then the energy comes back in the winter at high level, back through here, back into the plant, where we recover all the heat from the lights and the exhibitions and the people, if there were any people. There's a bit of a problem for the Earth Centre. I'll more on that in a second. But so we're recovering all of the energy that we can to use it as part of the system. Now, the Earth Centre has suffered from millenniumitis in that it was, I think, underfunded. The project needed about 100 million to give it a critical mass to make people go for the day. And they spent about 50 million, of which 25 to 30 went on regenerating the old coal spoil heap and landscaping the gardens. Future Systems' big arc building hasn't yet been commissioned or built. And so the centre hasn't got a critical mass that encourages the number of visitors that ought to go, because it is a very exciting and interesting half-day out. But it's a long way to go for a half-day out. It would have been a very, very good day out. And I just hope that one day the Lottery Commission will see sense and start to actually properly fund some of these things. I mean, say that if you have a dream, let's do it properly. Because all the people who were involved in the design and the creation of the Earth Centre became so embroiled in fundraising and trying to get matching funding going that they failed to deliver enough in the end, because all their creative energies were channeled down fundraising, which is very sad. It's also one of those lottery projects where I remember Max has had some of these, where you do what we call virtual stage D, because to achieve lottery application, you do a design, which you say this is, it has to be a RIBA stage D design, and you just don't get time to test it because you're not being paid fees. You're doing it on spec until the lottery approves the design, but you submit these great grand schemes which have to appear to be quite developed. And this is what happened on this project. We did this design pretty much by intuition, put it in for the lottery application. And about a year and a bit later, we got the funding. We were on site building this raft. About 8 weeks later, Molems were on site building it. And we hadn't even modelled it because we hadn't had any fees to do all the modelling. So everything that we've done has been entirely on manual calculations and just some very basic modelling, because we'd literally been paid about £2,000 by that stage to develop the systems, which is complete madness, absolute complete madness. It was a headlong rush. I mean, and thankfully we were then sponsored by EDAS to do some dynamic simulation work on it. But it is quite a difficult sensation when you arrive on a site and see this kind of building work going on, when you're thinking, hang on, I'm still just thermally modelling this to check that it works. And then, well, we knew deep in our heart of hearts that it did work, but we didn't know. In fact, the modelling showed that it works better than we thought. But and so what you've got here is a combination of concrete walls, which pick up the slabs from top to bottom, and blockwork walls. My biggest fear, being in Yorkshire, and the time of year the building was built, was that we found it very, very difficult to keep the water out. In fact, impossible, and the contractor in the end gave up, to the point where the labyrinth was about 2 feet underwater for about 6 months. And I was very worried when we set the thing going that it was going to have terrific problems with condensation inside, with the hygroscopic action out of the concrete. But in fact, we ran it for about 3 months while they were fitting it out, and we haven't actually had any problems with condensation at all, which has been an enormous relief, and it's now extremely dry down there. So subsequent to the project actually starting almost on site, we did detailed task modelling, and I won't go into too much detail on this, but we basically had the important thing to realise is that they aren't simple thing, although it looks quite simple. It's just concrete and block, isn't it? And you're blowing air through it, aren't you? So doesn't look that complicated, but there are some fairly key variables that you have to deal with, which is the air volume, the surface area, adjustments of surface weight, types of materials, the geometry of the air paths, and then looking at how it might perform in other parts of the world. And this is just some output from the predictive model, which suggests, this is the sort of idea about attenuation. This is the outdoor temperature here. This is the air as it moves through the labyrinth, starting up here actually, and gradually cooling as it goes through the stages in the labyrinth, till it discharges into the space at somewhere around 19 degrees on the peak day. It doesn't get that warm in Doncaster on our model, which is quite fortunate. So what you get then is, that's the external temperature there. That's the temperature 2 meters above the floor, is that line there, as predicted. And then the temperature at the ceiling is up quite a few degrees warmer, but it's just the displacement effect working and displacing the heat gains upwards. So what we were starting to show that with our arrangements, and in fact that was at this point we reduced the amount of area of walls and we reduced the number of traffic cones. In fact, we took them out altogether because we found we had enough capacitance in the structure to keep the place cool. And then just a comparison really of the CO2 generation as a result. Had we used a conventional overhead air conditioning system, we would probably have been somewhere up in this territory with energy consumption. With a less conventional displacement system, we might have been here, and with the labyrinth, we think we're somewhere around there. I'll zip past this because it's the important issue for me about this was, this is the Earth Centre as it opened, the Planet Earth Gallery here. I haven't got many good shots of it inside, but it's quite interesting that the installation artists who are working both on the photographic works and the acoustics became very interested in the labyrinth. The chap who was doing the acoustics has put lots of speakers and stuff down there, and you get these great booming noises coming out of the labyrinth as you're walking around the exhibition. Minotaurs and all that sort of thing. And Helen Sear, who's an amazing installation photographer, spent quite a lot of time down there and produced a whole series of photographs letting off all sorts of lights and effects. And this is actually down underneath the ground in the labyrinth. One thing just to add to that is that thermally the labyrinth needed to be about 1 metre deep, but we had to have the dampers down there for control, which meant we had to be able to get maintenance men down there, which meant with CDM that we couldn't have a crawlway, we had to have a walkway. So, and then we had to put emergency lights down there. So the most frequent visitors down there are the guys changing the bulbs on the emergency lights. But for that reason, we had to elevate the floor slabs to 1.6 metres and actually increase it by an extra 400 to make it friendly to maintenance men, which is obviously an entirely laudable thing. Okay. About the same time as this was going on, we were doing a competition in Melbourne, and this is just the last few slides. We did a competition for Federation Square in Melbourne with the famous Peter Davidson and Don Bates, who I think are reprobates who are well known around here in these parts. And we took, when we were looking, we won the competition, and we didn't have a labyrinth in the competition at the time, but we ran the model from EDAS on Melbourne weather to see if we moved the Earth Centre to Melbourne, what would happen. And what we found was, even with the much higher outdoor temperatures, if we added a bit of evaporative cooling in, we could maintain the labyrinth outputs at around 25 degrees, which we felt might have some good contributions to make to trimming the tops off this air conditioning load in Melbourne. Particularly as the scheme that we were looking at, which is, the scheme is here. I don't know how many of you are familiar with this. Peter and Don came here, I think, and lectured. So did you have a lecture from Peter and Don on the scheme? It was at the RBA. This is downtown Melbourne. This is Flinders Street Station, which is sort of one of the part of the hub of the town. Over here is the MCG cricket ground and the tennis centre, and the CBD sitting somewhere here. Currently, there's no linkage between this main street in the town and the river. It's at railway tracks, and so they basically covered over the railway tracks and are building this large square, which is a Federation Square, which is there to celebrate the 100th anniversary of the Federation, or is it 200th? I should know that, shouldn't I? There's a large museum here, the Museum of Australian Art, and a Cinemedia Centre. And down the centre was a continuing a kind of an important linkage that runs down a street that runs down the centre of Melbourne, pedestrian, is an atrium that kind of opens up down to the streets. This is west facing. And there's another view of the main square, these shards, which are very contentious because of the way they address the cathedral. And closing in here, there's, as I said, the square there, pub down here, and the main facade. And we actually handed over the engineering to a local firm for most of the buildings, but we kept involved in how we were going to deal with the main atrium spaces, the glass atrium spaces, because we were always pretty concerned as to about how we were going to environmentally control them, because it is the Australian way, because energy is incredibly cheap in Australia. The Australian way is to air condition things from above, and what the hell. Their energy is about 2p a kilowatt hour compared to sort of 6 electricity, compared to about 6p here. And so this is, again, just to clarify where things are. It's the Civic Plaza, here, which is rises up from the station up by about 4.5 metres, before we kind of amphitheatre space here, and then this main atrium that we're looking to condition with the other elements there. And I took along my reports from the Earth Centre, and they loved the idea of a labyrinth. The client sort of fell in love with the idea and said, we really want one of these, because Sydney was supposed to have the Green Olympics, and they didn't, because they basically bottled out on all the funding. This is how the story goes. And Melbourne is very competitive with Sydney, and so Melbourne said, if Sydney aren't going to be green, we're going to be green. And so they took this on as a kind of iconic thing for the project. And the project's gone quite a long way over budget. Surprise, surprise. And it has survived unbelievable culls. Everything else on the project has been hit really hard. But if anybody goes into, apparently the quantity surveyor starts every Monday morning meeting, says, right, now the labyrinth, everyone just goes, shut up. Because they know he's not going to be allowed to take it out. And it has survived, it's now been built. It's now under construction, or it's nearly finished. And so the labyrinth sits here under the main plaza deck, and the main atrium is here. And the principle we've got is slightly different to the one at the Earth Centre, in that we have a plant that blows the air through the labyrinth and controls the conditions of a labyrinth. And then we have 3 other plants which are basically sucking the coolth or the heat out of the labyrinth. One goes to the atrium, but if the atrium doesn't need labyrinth power, the air can then be sent to other areas of the building where there are more year-round air conditioning loads, such as auditoria and theatre spaces. The labyrinth isn't ground coupled, which was a big issue for us at the beginning. We thought,